Hello, Professor. My name is Joshua Rodriguez. My lab partner is Carlos Brodowska, and today I'm presenting my Project 3, which is the line following robot. So as you can see here, I have two include statements, the st.int.hex file, which is going to include some of the values we're going to use for our finite state machine, and the tm4c123 hex file, which is essentially going to grant us some additional data for some of the defined statements. So as you can see here, I have several defined statements. I have defined statements for port B, which is going to be used for the motor, as you can see with the motor out. Port A, which is going to be used for the IR sensor, and port F, which is going to be used to is going to be used for both the buttons, for the race button and the stage button. So as you can see, I have several modules: the disable interrupts, enable interrupts, and wait for interrupts, which is obviously the ones we already used before. The GPIO port F handler, which is essentially going to handle the interrupt buttons for the race and stage button. Then we have port B init, which is going to initialize and handle the step promoters. The port A init, which is going to handle the IR sensor, and the sys-stick handler and the sys-stick init, which is going to handle the delays for the lab. So as you can see here, we also have several different types of global variables. Input, which is going to represent the inputs for the finite state machine. The S, which is going to represent the state for the finite state machine, and pos and lim. This is going to be used to control how the DC motors function in this lab. So as you can see here, for the finite state machine, we have out, time, and next. Next is obviously going to hold the values, or it's going to basically, depending on what the value of next is, it's going to determine what state it's going to go to. Out is obviously going to have the output of the whole thing, and time, which is going to represent how long the delay should be for each stage. So you can see here, I have three states: SO, which is step 0, which is the first state; S1, which is step 1; S2, which is step 2; and S3, which is step 3. So as you can see, for this finite state machine, I have these specific outputs. So first of all, you should know the inputs. The first one being move, the second one being forward, and the third one being reverse. So based on whatever the input are for these, it'll essentially do several of the following, including either move forward or move back a few steps. So these are the outputs I have for the finite state machine, because these are essentially going to determine how the DC motors move. I also have one for all of the delays, as well as all these different states. So depending on the inputs, it'll enter a different state. So as you can see here, I also have my main, and I have all my initializing statements. You should also keep in mind that it's sys-stick init and the finite state machine time to basically, depending on the state, it'll determine how long the delay is. So many of these instances will just be one. Then I have also input set to 0x0, which is essentially going to act as the input for the PF4 and PF1 buttons. I have pos equals 0 and the lim equals 0, which is going to determine how many steps the motors are going to take. And then we have while for interrupt. So let's go to the port F handler. So you see, whenever we have set pos equal to 0, essentially this is going to determine how it essentially represents the amount of steps that have already occurred. And then whenever PF0 is pressed, that means that it'll change the input to 0x03, and then it's going to set lim to 9216. Essentially, what this is going to do is that this is going to determine how many steps are supposed to be taken. And because of this, that means that it'll go 180 degrees counterclockwise 9 times. In other words, it's going to go forward. Then we also have else if GPIO port F RIS R0x10, which is when PF4 is pressed. And this triggers it to be inputs equals 0x05, and this is going to trigger lim equals 512. And essentially what this is going to do is going to make the device go 90 degrees clockwise 1 time, so it's going to go back for a few steps. And then we also have our GA port ISRR, which is going to reset the whole interrupt. Then we have port definition. The only things you should keep in mind is that this is going to initialize the ports for the stage button and the race button. And we have PF0 and PF4 and PF0 unlocked. And also another thing to keep in mind is that we have this set priority to 2, and we enable interrupt on 32. Then we have port B init. So basically this is gonna this is going to open up the ports so that we're able to use the DC motors for port B. So you can see here we have PB7 to PB0 all open with the 0xF, and we also make sure to set up the system clock. Then here we also have port A. So port A is going to give inputs to PA2, which is essentially going to act as the ER sensor for this lab. So going further on, so whenever GPIO port A RIS 0x04, essentially what this means is that whenever the IR sensor detects something or detects an obstacle, it'll set the input equal to 0 and set pos equal to 0 and lim equal to 0. Essentially what this does, it essentially stops the entire vehicle from moving. Then we have the 6-tick handler, and essentially this is gonna basically do what it's supposed to do and generate the interrupts for the 6-tick. So whenever pos equals lim, essentially this means that whenever the steps equals the amount of steps taken, so in other words, when the motor or whenever the DC motors are finally done moving, it'll set the input equal to 0x00 and thus putting everything to a stop. However, if this isn't the case, then it'll simply continue going through the steps or the stages, as you can see with the s equals fms.x next input, also takes in the delay and the motor out, so essentially motor out is equal to finite state machine s.out, which is going to be equal to the output. It's going to take in the output to the finite state machine, and pos plus equals 1. So essentially the pos is going to continue incrementing up and up until it reaches the limb. So only does it, when it reaches the limb, does the DC motor stop. So pos is essentially the amount of steps that have been taken, and limb is the amount of steps that are supposed to be taken. That's the maximum limit we should reach. And then if we continue going down, we have our sys-tick init, which is essentially going to initialize this whole entire system clock. And we also make sure to set the priority set to free.